I've been talking about using Laplace transforms to solve differential equations for some time. And finally, we're going to get around to it. In the first section of this chapter 6, we basically learn what Laplace transforms are through this definition as an improper integral and the inverse transforms. We went to section 6.2 in order to find fast ways to take Laplace transforms so we wouldn't have to go back and evaluate improper integrals. And we found some techniques that would do that. And paramount in those discussions was the Heaviside unit step function. Now we've got all the tools we need to solve differential equations, except we need a little bit more. Theorem, because differential equations have in them derivatives. And so I need to know how to take the Laplace transform of a derivative. And the theorem says, basically, we're adding all the details. Suppose f of t is continuous. Suppose f prime to t is piecewise continuous. And it would say, on every finite interval like that. And suppose this guy is exponential order alpha. All right, if all those conditions are met, then you can say the following, that the Laplace transform of f double prime of t, well, let's do f prime first, okay, is equal to s, f of s, minus f of 0. What you do, if you want the Laplace transform of the derivative, you take f, that's the Laplace transform of him, multiply by s, and subtract the value of the function at 0. Proof? See the book. Notes, all right? I proved it in the notes. I'm not interested in reproducing that here. So there's how we take the Laplace transform of the first derivative. If we want the Laplace transform of the second derivative, then we need to assume more. We need to assume that this is continuous, and this is continuous, and the second derivative is piecewise continuous, and this one is an exponential order, and this one is the same exponential order. Then, right? And I'll leave you to read all those details. It says now that the Laplace transform of f double prime is equal to s squared f of s minus s f of 0 minus f prime 0. It says that. There's how you take the Laplace transform of the second derivative of a function. You take the Laplace transform of the function, and you multiply by s squared. Then you subtract the value of the function at 0, multiply by s, and then you subtract the first derivative at 0. Now this is relatively easy to prove, because we can prove this by doing that. All right? So let's prove that, because that's much more simple. F double prime of t. The top line says, if you want the Laplace transform of the derivative of anything, and this is the derivative of the derivative, it says you take s times the Laplace transform of f prime to t, and then you subtract f prime to 0. That's what this would say if I think about f primed. But how much is this? Oh, we use that again. You'd have s f of s minus f of 0 minus f prime 0. And that is indeed what you're looking at here. Can you fathom a guess what it would be if it were triple prime? You can probably see the pattern. It would be s cubed f of s minus s squared f of 0 minus s f prime 0 minus f double prime 0. And that's what it is. So we now have formulas for taking Laplace transforms of derivatives. Let's now go and solve some differential equations. Here's the first one. Y double prime 2y prime plus y is equal to t. There's So I'm not going to solve a differential equation. I'm going to solve a initial value problem. That one. And I'll tell you why after. So what we do is we say, let's take Laplace transforms of the left-hand side and the right-hand side and put them equal. All right, and then we'll use the fact that Laplace transform is a linear operator. And so we can take the Laplace transform of this, plus 2 times Laplace transform of that, plus the Laplace transform of that. So let me write that. The Laplace transform of y double prime, plus 2 times the Laplace transform of y prime, plus the Laplace transform of y, is equal to Laplace transform of d. That's 1 over s squared. Right? Now I'm going to put a lot of detail in this first example. That way I can kind of leave out in future examples, but I want you to see every little detail here. In fact, I would not normally write this line. Right? Okay, so let's go. It says Laplace transform y double prime. There's my formula right there. It says you write s squared times the Laplace transform. What? That's big Y of s. Big Y of s is the Laplace transform of y. And then it says, oh, you're supposed to write minus s times the value of the function at 0. Oh, that was 0. Minus the first derivative at 0. That's what. So that is coming from this one onto the next one. 2. We need Laplace transform of y prime. Now we use this one. It's s times y of s minus value function 0, 0, plus y of s equal to 1 over s squared. So notice what the Laplace transform has done. It has removed all of the derivatives. What have you got? You've got an equation here with y of s. What you can do is solve this equation for the Laplace transform of the unknown function that satisfies our problem. So let's do that. Y of s. I'm going to do more than I would normally do. I'm going to take the y of s's on the left, and I'm going to factor them out. S squared. That one. Plus 2s. And plus 1. I'm going to take all the terms that have no y-s's over to the other side. I would have 1 over s squared. That one. I would have this one going over plus 1. And that's it. Now I'm going to divide by this. Y of s is equal to 1 over s squared plus 1 over s squared, 2s. I now know the Laplace transform to the solution of this problem. All I have to do is take the inverse transform of this, and I will have my y of t. So contemplate that. How are you going to find the inverse of this? There's 2 things you could do. One, you could bring these 2 to a common denominator, having a 1 plus s squared, and then take the s squared down. 2, you could take this one over this one, and this one over this one. Ultimately, you're going to have to partial fraction. And I told you that when you solve differential equations with Laplace transforms, almost every problem has got partial fractions. And you're going to see that from now on. Partial fractions, partial fractions, partial fractions. So the question is then, which would you prefer to do? This one over this one, and this one over this one, or common denominator, and then answer this one over this one, this one over this one. Usually turns out to be more efficient. So I'm going to write that. 1 over s squared By the way, that bottom does factor, right? Into s plus 1 all squared. Plus, what was the other one? 1 over s plus 1 squared. So there it is, right? Now, the reason I like that was this is already in partial fraction form. All I have to do is partial fraction this one. Compare that to if I had not done that and done the other possibility, I would have 1 plus s squared over s squared, s plus 1 squared. You'd be partial fractioning that as opposed to partial fractioning this, because that was taken care of. So I've reduced, I don't have this s squared on top. To me, that's made it simpler. But you do now have to go get partial fractions for this. All right? And I'm going to tell you what they are, but I don't want to go through it. I'm going to tell you that if you partial fraction that whole thing, including this, you get 2 over s plus 1 squared minus 2 over s plus 1 over s squared plus 2 over s plus 1. Right? Is that reasonable? So in other words, these terms are coming from there. If you partial fraction this thing, you'd have an over an s squared, an over an s plus 1, and an over an s plus 1 squared. That's what you're going to do, okay? And so this one is this one, this one is this one, this one is this one, and this one, whatever it is combining with this one to give that, right? So that's the partial fraction here. Now we've got it invert. So y of t is equal to the inverse of this. All right, let's do the easier ones first. The inverse of this is minus 2. The inverse of this is t. The inverse of this is 2 e to the minus t. What about this? Oh, I forgot to bring my overhead, all right? Everywhere I look in here, it's s plus 1s. So why don't we use that property that said, let me write it down. It said that if you got f of s minus a here, and you want to go back, it is e to the at, the inverse transform of the f of s. You get rid of the a, right? So what are we going to write? We're going to write for this one then, plus 2 e to the minus t, the inverse transform, and drop the plus 1s, 1 over s squared. And so what do I get then? This one, plus 2 e to the minus t, and this one is t. There's our solution. Now, let me back up and say a few things. 1. In taking here and saying, I'm going to take the transform of these, I made an assumption. I made an assumption that because I wanted to take the second derivative, there was a theorem that said, if the function is continuous, and its first derivative is continuous, and its second derivative is piecewise continuous, and if the function and its first derivative are of exponential order, then you can do this. And a similar thing for this. So I made assumptions in taking Laplace transforms that I could use those formulae. I've got a choice now. I can now go back and say, hey, now that you've got this function, ask yourself, is it continuous? Does it have a continuous first derivative? Is it of exponential order? That's one way to verify it, or say, I could do what I did. The other possibility is simply say, go back and see if this satisfies your problem. Plug it into here, check this, and see if it works. So the problem is really not quite done until I do one of those things, but I'm never going to do it. We're just going to accept this. Now the continuity part and the function and its derivative, that's not a problem. Because if you solve a second order linear differential equation, we saw back when you do that, the function will be continuous, the first derivative will be continuous, and because this is continuous, the second derivative will be continuous too. So all that I'm really assuming is the exponential order thing. But we're not going to bother saying that every time. All right, those remarks out of the way. What I want to review is what Laplace transforms does. Notice that when you take the Laplace transform, the transform uses these initial conditions right in the first line. If I were solving this problem with chapter 15, I would go find me a general solution. It would contain two parameters, and I would use these conditions to find out values for those parameters. The Laplace transform says, no, I'm using them right away. First line. Right. So it does that, and it gets rid of all the derivatives, gets you an algebraic equation to solve for y, which you do, and then you have to invert it. There's only, in my opinion, one difficult part, the inversion. That once you get the y of s, is now you've got to go and get its inverse. All the rest of that is really, really straightforward. Agreed? So that's Laplace transforms at work. Let's do another example. And I'll cut down on the amount of writing, because it's a bit laborious. So consider this example. Y double prime plus 2y prime 5 prime is equal to e to the minus t. Y at 0 is 2, and y prime at 0 is 0. Again, an initial value problem, which kind of prompts the question, is that all Laplace transforms will handle? And the answer is no. My third example is going to say it'll handle boundary value problems, and the last example will say I can produce general solutions too. Right? But I want to practice with two initial problems to begin with. All right. So we say, taking, I assume that's a plus sign. Let's make sure. 2 plus y. So taking Laplace transforms, for this one, it is s squared big Y. I'm not going to like what I did right over here. Wrote big Y of s, big Y of s, big Y of s. That just makes it look more cumbersome. All right? I'll drop the big Y's until I get down to here. About the big of s's until I get to here. Then I'll, right? What do I make? All right. And then we got, what does it say? Minus s value function 0, 2. Minus first derivative 0, 0. So that formula I erased there for second derivative, that's what it is. Plus 2. Laplace transform y prime s big Y minus 2 plus 5 big Y equal Laplace transform 1 over s plus 1. So exactly the same as there. All I kind of did was drop the big of s's, and I didn't write this intermediate line. Right? Now we want to solve for big Y. I'm not going to do this like I did here. I'm going to simply say, first thing, take anybody with a note big Y in it to the other side. Pin's already over there. I have this one. That's a 2s. I have this one. That's a 4. So there to the other side is all the non-big Y terms. What I'm now going to do is take the big Y terms and factor them out, put it here, and then put it down there. I'm going to put it straight down there. I got an S squared. I got a 2s. I got a 5. Now, unfortunately, I shouldn't use 5s. All right? Let me make sure that my 5s are distinctly different than my S's. There. So, right there's my transform. All I now have to do is invert it. Invert it. Choice again. Do you want to bring this to a common denominator and then put that downstairs, or do you want to put this one over this one, and this one over this one? My choice, the second choice, just like in that. Before I go there, I want you to notice something. Tell me about this, and tell me about this. Comment. Where have you seen those things before? Almost. Answer. What's the auxiliary for this? M squared. 2m and 1. S squared. 2s plus 1. What's the auxiliary here? M squared. 2m and 5. S squared. 2s and 5. Does that always happen? Yes, it does. So take a quick look. All right? Take a quick look when you get to here. That looks right coming from here, thinking about the auxiliary equation. All right, back online here. I said what I would do if I were doing this one, I would write 1 over s plus 1 and s squared plus 2s plus 5 and then plus 2s plus 4 over s squared plus 2s plus 5. Now if I started to look ahead a little bit, right? Partial fraction in this thing, not happening. This thing does not factor. In fact, if I looked at the discriminant, it's negative. This is a quadratic guy, but we saw how to handle that, right? So this guy is ready for processing, okay? That's why I didn't want to take this one, common denominator over all that one, because that one is ready. All I have to do is work on this one. I will have to partial fraction this one, all right? I'm going to tell you what the answer is. If you do it, right? If you partial fraction this thing and combine it with that one, you get the following. 1 over 4 over s plus 1 plus 7s over 4 plus 15 over 4 all over s squared and 2s and 5. But you have to do that, right? So you have to partial fraction this one, and that term is coming from that one, and then there's 2 terms coming from here, and when you combine it with that guy, you end up with this thing here, right? So let me make sure, okay, that looks okay. All right, so all we now have to do is invert. First term, not a problem. So y of t is equal to, inverse of this, 1/4 e to the minus t. Now we have to work on this one. Let's write temporarily plus. Let's pull out the quarter, inverse transform, and let's start to work on it. Because of this quadratic, we saw last time that what we should be doing is completing the square. So let's do that. S plus 1 squared, and then we're going to need a plus 4. So that's the square completed bottom. We've got to get the top in the same form. We've got a 7, so we're going to have to write 7 s plus 1. And that's giving 7, but we want 15, so we're going to have to put in 8 here. So that's prepared the way for the inverse. So now let's take the next step. 1 over 4, e to the minus t, 1 over 4. We can now get rid of these plus 1s by using that property that I had about a minute ago when I erased it. E to the minus t, the inverse transform, and kill the plus 1s. And now those are sines and cosines. So we can finally finish. 4 e to the minus t, 1 over 4, e to the minus t. First one is 7 cosine 2t. The second one is 8 sine 2t, but it needs a 2 fix. So that's going to be then a 4. So there's the answer to that one. Similar to the first one. Agreed? Same process. Only difficulty was again, Once you got to here, it took me 2 lines to get to here. The rest of it is the inversion process, which is always the difficult part. I made a claim a moment ago that Laplace transforms can also handle boundary value problems. Let me show you what I mean, because I haven't used that word too often. Consider this problem of solving y double prime plus 9y is equal to the cosine of 2t. And I tell you that y at 0 is 1. And I tell you that y at pi by 2 is equal to negative 1. So you can see what it's not an initial value problem. This up to here looks like an initial, but an initial problem would have y prime at 0 being something, and that's what the last 2 problems have. This problem is saying, solve this differential equation between 0 and pi by 2. Solve it on that interval where there's the value of the function at the left end, and there's the value of the function at the right hand end. Laplace says, I don't like you, okay? Laplace says, I love initial value problems. Laplace says, I want y prime at 0, okay? Right? So what we're going to do then is give it a name. We're going to say, let A be equal to y prime at 0. Give it a name, unknown at the moment, and later on, we'll find out what it has to be. So proceeding then, with that, taking Laplace transforms. For the second derivative here, s squared, big Y, minus s times the value of the function 0, 1. Minus the first derivative of 0, a, plus 9 big Y equal plus a cos s over s squared plus 4. Solve for big Y. Big Y is equal to s squared plus 4 plus u over a plus s all over s squared plus 9. There. All right? All I have to do is invert it. Again, I would not common denominator this over that. I would take this one over this one, and this one over this one, because that one is ready. This is my problem child. So we'll write that. S over s squared plus 4. S squared plus 9. Plus a plus s over s squared plus 9. So all we have to do is partial fraction that one, and then join one to this with that. Right? So you have to go through that partial fraction decomposition. And if you do, I calculated it to be 4s over 5a all over s squared plus 9 plus s over 5 over s squared plus 4. Right? So that's what I have got written down. 4s over 5 plus a, and then s over 5. All right. 4s, wait, that doesn't, 4s plus a. Plus a. There. So all we have to do now is invert. And we'll get our y of t. We can look on forward. If we get the y of t, then we can now impose this condition to find out what the a will be. So y of t is equal to, for the 4s over 5 over this, the 4 over 5 over front, 4 over 5. And then s over s squared plus 9, that's a cosine. Cosine 3t. Then we've got a over, that's a sine, plus a, the sine of 3t, but it needs a 1/3. Then we have this one, which is another cosine. A 1 over 5 be cosine of 2t. 1 over 5 be cosine of 2t. There it is. So now we can say, but minus 1 must be y at pi over 2. So let's plug in pi over 2. Put in pi over 2. We'd have the cosine of 3 pi over 2. That's 0. We'd have the sine of 3 pi over 2. That's minus 1. Minus a over 3. Then we'd have the cosine of pi. That's minus 1. Minus 1 over 5. So therefore then, a over 3 is equal to 1 minus a fifth. That's 4 over 5. So a then is equal to 12 over 5. I hope, and that will be our answer. Twelve over 5. All right. I got a 4 and I got a 1. That's all right. So there then is a boundary value problem solved. We simply had to do this. Give y prime to 0 a name, then we could proceed, and later we could find it. I want to now demonstrate that we can actually find general solutions using Laplace transforms too, which was what the most problem thing was back in chapter 15, right? General. So consider this problem. Y double prime minus 2y prime plus 4y is equal to e to the 3t. Find a general solution of this differential equation. All right? We don't have y0 and we don't have y prime 0. We'll have to get those names. Let y at 0 be equal to a and y prime at 0 be equal to b. Just like in the last problem, but there's two of them unknown now. So if we take transforms, we will get s squared, big Y, minus as, minus b, minus 2s, big Y, minus a, plus 4, big Y, is equal to 1 over s minus 3. We solve for big Y. Big Y is equal to 1 over s minus 3. You're over there. What else? That's going over. Plus as. That's going over. b. That's going over minus 2a. So let's put those in parentheses. Over s squared, 2s, and 4. So all we have to do is invert this, and we will have our general solution, and there are at the moment 2 arbitrary constants. We know actually what they mean. This arbitrary constant A means value of solution at 0. B, value of first derivative at 0. But, all right, let's think about inverting. Again, I would do this. This one over this one, this one over this one. So I would rewrite it as 1 over s minus 3, s squared minus 2s plus 4, plus as, b minus 2a, over s squared minus 2s plus 4. Now we're going to do some thinking. Otherwise, we're going to be doing all kinds of unnecessary calculations. We want to think, right? That's the key to calculus. Think! Let's think. If I partial fraction this, I'm going to get this, and then I'm going to get a cs plus d over this, right? A cs plus d over s squared minus 2s plus 4. And then I've got this. I will invert this, and then I'll join these guys together. I'll join this c with that a, and I'll join this d with that b minus 2a. All right? Now, I will know the c and the d, right? When I partial fraction this, I'll know the C and the D, so I'll put that C here, all right? All right, so this will be a number, put in there, A plus that number. And then I'll have this plus this number A, okay? But remember, I'm looking for a general solution. Right now, I interpret what A and B were a minute ago. Do I care? No. All I want is two arbitrary constants. So what I'm going to say is, if I were to do this partial fraction decomposition, I would end up with something that looks like that. If I find out exactly what the C and the D are, and I combine them with this, then I would have something in here with A's and B's, or A's and some numbers, and B's and A's and some numbers. Do I care about the A and the B? No, I don't. I'm simply going to say, if I did all of that, I get something here and something here. Let's call it C and D. Then I only get this one. But this one, I can get by handy-dandy cover-up. All I have to do is to cover that up and put in a 3. If I put a 3 in, I get 9 minus 6 plus 4. That's 7, 1 over 7. So we're going to say then, y of t is inverted. 1 over 7 e to the 3t plus the inverse of, let's just write temporarily, cs plus d over s squared minus 2s plus 4. All right? So all we have to do is invert that last guy. And how are we going to do that? Is it a factor? No. What are we going to do? Complete the square. All right. So here we come. 1 over 7 e to the 3t inverse transform, completing the square. S minus 1 squared plus 3. Top, I need s plus minus 1, and then I'll have plus d plus c, right? Oh, what do we call that one? E, okay? Just another constant, right? So now, here we come, 1 over 7, e to the 3t. We get rid of the minus 1 by writing e to the t. Inverse transform of cs plus e over s squared plus 3. Getting there. All we have to do is this one now. 1 over 7, e to the 3t, e to the t, and the inverse transform. Cs over, that's a cosine. C, now over down, C, cosine of root 3t. Then for this one, we would have an e, sine of root 3t. And then it'd have a root 3 in the bottom, and I'll call that f. There it is. There's my general solution. What's this? This is the general solution of the associated homogeneous equation, and this is the particular solution of the non-homogeneous equation. But we didn't get it that way. We got about Laplace transforms. So Laplace transforms are handy. Initial value problems, loves them the most. It can handle boundary value problems. That wasn't bad. And it can produce general solutions. But you can make life easier by doing the kind of thing I did here and not worry about what the names of the constants are. So that's how we solve differential equations. All we've done so far, however, is solve the differential equations that we did back in chapter 15. The right-hand sides of all three differential equations today have been nice. And remember I said at the beginning of this chapter, the power of Laplace transforms comes when the right-hand sides are not continuous functions or they're piecewise defined. So we've yet to get to that. That starts at 6.4, but I have something more to do at 6.3 next day.